Hi, I am Cat017, and today we are going to learn about the digital world, starting with the 8-bit processor. And subscribe if it's good. Let's begin. We are plunging straight into the absolute core of premium industrial automation and mechatronics. We're going to completely deconstruct the impossible performance you see in high-end semiconductor pick-and-place machines. We'll detail exactly how engineers bypass traditional digital sampling limits to achieve sub-microsecond precision and nanometer-level accuracy using proactive, predictive observers. It's a fascinating leap from vintage 8-bit logic to today's multi-core gigahertz execution.
As our system boot-up sequence completes, here's the roadmap for this deep dive. 1. The limits of standard control. 2. Field-oriented control and predictive observers. 3. Zero-lag PWM synchronization. And 4. Stability for nonlinear loads.
Alright, part 1, the hard limits of standard control. Think of a standard cascaded control loop as the central nervous system of a machine. We typically have 3 primary layers here. The outermost layer is the position loop, feeding into the speed loop, which then feeds directly into the innermost layer, the current loop running right there within the microprocessor. Because this current loop acts as the absolute physical foundation of the machine's mechanical output, its bandwidth essentially dictates the performance ceiling for the entire system. If the current loop is slow, everything else is compromised.
But here is exactly where we hit a massive physical wall. When we execute a discrete proportional integral, or PI calculation, in that current loop, we immediately face the fundamental sampling theorem. To avoid aliasing, which is basically when your system generates false phantom signals, a measuring device must sample an analog signal at a rate more than twice its highest frequency. That's the Nyquist limit. But taking those samples and crunching the math takes time. This inherent calculation dead time delay, also known as transport lag, physically prevents the system from instantly suppressing high-speed mechanical disturbances. This creates a classic agonizing dilemma for control engineers. If you play it safe and set a low proportional gain, the response is incredibly sluggish. It might take upwards of 15 microseconds just to settle, often leaving a frustrating offset error where the motor falls short of the target. But if you try to fight that transport lag by aggressively cranking up the proportional gain, the whole thing breaks down. The step response curve erupts into violent, high-frequency tracking oscillations. The system just endlessly hunts for the target rather than snapping cleanly into place.
So, why do standard PI controllers completely fall apart at these ultra-high speeds? Well, it's a perfect storm. First off, slower sampling rates naturally result in fewer data points, which creates much larger integration calculation errors. Second, you have to deal with integral windup. Because the integrator keeps a running sum of past errors, a constant tiny error can accumulate into an extremely high value, which triggers erratic and potentially damaging machine movements. And finally, if you assign your function blocks to slow processing time slots, the math isn't recalculated fast enough. That delay acts as a severe lag element. Ultimately, reactive PI control is just fundamentally unequipped for ultra-high-speed dynamic environments.
Moving on to part 2, field-oriented control and predictive observers.
If you consider the physical structure of a 3-phase permanent magnet synchronous motor, trying to control that alternating current directly is a mathematical nightmare because the parameters are constantly fluctuating. However, we can use a brilliant workaround. We mathematically map the transition from that highly complex ABC stator coordinate system into a synchronous DQ reference frame. This transformation is an absolute game changer because it drastically simplifies the physics the processor has to compute. This is the magic of field-oriented control, or FOC. It elegantly decouples the magnetic flux. It separates the magnetizing field onto the vertical D-axis and pushes the actual torque-generating field onto the horizontal Q-axis. Because they are placed on these perfectly orthogonal axes, they literally do not influence each other. This allows the system to adjust the motor's underlying magnetization and its rotational torque completely independently of one another. And that brings us to this beautifully simple torque formula. By shifting the math into this synchronous DQ coordinate frame, controlling a highly complex, nonlinear AC motor suddenly becomes as straightforward as driving a basic brush DC motor. The torque output becomes directly and solely dictated by the Q-axis current. With the math simplified, we can now introduce our secret weapon, the predictive state observer. We place this predictive engine in parallel with the main control loop. The digital signal processor utilizes continuous state-space matrices to actually calculate the required electrical trajectory ahead of time. By being proactive instead of reactive, this calculation allows the current to rise instantly, hitting tight 50 nanometer tolerance bands in less than 850 nanoseconds, totally bypassing traditional transport lag. Let's look at section 3, zero lag PWM synchronization. Of course, having the theory sorted out is great, but we have to ground these predictive equations in raw hardware execution. At the heart of the drive's power stage is pulse width modulation. To completely eliminate jitter without adding a single nanosecond of lag, we meticulously align our hardware interrupts. We force the processor to execute its control loops exactly at the absolute peak and the absolute trough of a high-frequency triangular PWM carrier wave. It's a highly synchronized, microsecond perfect ballet between the digital grain and the analog power transistors.
Furthermore, we can't just read sensor data whenever we feel like it. If our analog-to-digital converters are taking turns reading data in a multiplex time sequence, our temporal view of the machine becomes completely skewed. To achieve true ultra-high precision, we mandate simultaneous sampling across all channels. Every sensor snaps its data at the exact same instant, feeding the predictive controller a perfectly consistent, unified snapshot of the machine's physical state.
The payoff for this extreme level of hardware synchronization is massive. By snapping the ADC sample point directly to the center peak of the triangular wave, all that nasty high-frequency switching ripple noise, which is localized on the voltage transitions, naturally cancels itself out. You filter out the noise without ever having to introduce a software low-pass filter, which would inevitably add processing delay. Plus, this precise duty cycle adjustment gives us incredibly high-resolution command over the power stage, carving out a flawless, zero-lag execution pathway straight from the DSP down into the motor coils.
Finally, Section 4, Stability Secrets for Nonlinear Inductive Loads.
So, we fixed the digital side, but as we push our proportional gains to the absolute maximum to aggressively reject physical disturbances, we slam right into physical reality, the mechanical resonance limits of the machine. The physical frame itself begins to flex. If you've ever been on a factory floor and heard a servo motor suddenly start shrieking, this is exactly why. Pushing the gain too far causes the motor to make aggressive noise, and the mechanical load violently oscillates.
Control engineers face a really brutal fundamental compromise here. Do you want a high-gain, incredibly rigid system that rejects disturbances instantly but shakes itself to pieces? Or do you want a low-gain, heavily damped system that runs incredibly smoothly but completely loses its ultra-high-speed precision? Standard PI tuning effectively forces you to pick a point on this sliding scale of compromise.
This is where Advanced Position Control, or APC, steps in to save the day. Modern premium drives use APC modules to intelligently bypass this conflict entirely. Utilizing feed-forward nonlinear dynamics, APC lets you maintain that massive speed control gain to suppress disturbances instantly, while mathematically identifying and filtering out the specific resonant frequencies of the mechanical load. You get all the structural rigidity with none of the destructive vibration. To squeeze out that last drop of performance past the stability limit, we use our final tuning weapon, jerk. Jerk is quite literally the rate of change of acceleration. If your tuning hits a strict stability wall but the system is still experiencing following errors, you can inject massive jerk values into the motion profile. This smooths out the harsh beginnings and ends of the acceleration curves, heavily reducing peak following errors without sacrificing one bit of the control loop's overall bandwidth. We have fundamentally bypassed the transport lag of traditional PI controllers today by perfectly marrying predictive state-space math with hyper-synchronized hardware execution. But honestly, it leaves us with an incredible question to ponder. As our digital processing scales higher and higher into the gigahertz range, what happens to our mechanical systems when our digital prediction completely outpaces the speed of the physical sensors themselves? It is an absolutely fascinating frontier for mechatronics. Thank you for joining me on this explainer. Keep learning, and I'll catch you in the next deep dive.
Thanks for watching, and please like, share and subscribe for such more content and appreciation. Make sure to comment your questions.